So hello and welcome, everybody. I'm Daniel. I'm heading the Deep Learning Center at Volkswagen. Volkswagen, for those who don't know it, is a mobility provider. So we don't manufacture cars, we provide mobility solutions. I'm part of the Volkswagen Data Lab, which is located in Munich, and I want to do three things. I want to first of all give you a basic idea what a data lab actually is. And then I feel myself a bit on a mission to explain people what AI actually is. So I will go a bit deeper in terms of AI. And finally, we'll demonstrate some use cases we are working on where we really try to transform traditional business by means of AI. So, what is the data lab? The data lab is the center of excellence, so to say, in terms of machine learning and AI for the whole Volkswagen Group. And when I talk about Volkswagen Group, I talk about 600,000 employees worldwide, and we have several brands. We work for VW, for Audi, for Seat, MAN. I think I did projects with almost every brand except Lamborghini for some reasons. We did not projects with Lamborghini so far. So our business is to extract meaning from data across the whole value chain. We will see that in a second. We have 5 main pillars within the data lab. We have, first of all, the so-called advanced analytics team, which is basically doing traditional data science stuff like sales, forecasting things, recommendation engines, and things like that. We have a special team for everything related to natural language processing, so everything related to speech and text. We have a specific team for deep learning, where I'm responsible for. And then we have 2 very cool things. On the one hand, we have a quantum computing team, so a team who is really working on this very new topic. And let's see in 10 years if it really we will have a return of invest here. And we have the AI research team. So we have a team of roughly 30 researchers who do fundamental AI research. And that's quite a unique thing for an IT department within such a huge company. So I already told you that we work along the whole value chain. We did projects in technical development, for example, with racing, with the guys from motorsports. We do a lot in production and logistics, and we are heavily involved in projects in sales and after sales, but also in mobility, so connected car problems, autonomous driving. We are not in the lead for autonomous driving, but do some cool stuff here as well. So that's a basic overview about the data lab. And now let's touch this point of artificial intelligence. So I think everybody is talking about AI, and I think everybody have a very different understanding of it, and let's try to order it a bit. So from a very top level point of view, you have 2 main pillars in artificial intelligence. On the one hand, the left side is this very human-driven kind of artificial intelligence, where you try to copy the human, where you try to create systems that think like humans and act like humans. So this is a very Japanese way of thinking about AI. The Japanese are super strong here. We also work in this domain, but we are more related to the right wing, and this is rational systems. Some call it rational agents. So we have a system or a piece of software that represents a process, represents some real object. So it measures data, makes a rational decision, and acts. That's the rational definition of an agent. And how can it make a rational decision? Based on a mathematical function. So we have to equip these agents, these rational agents, with a tool set. And for me, this tool set is AI. So if you ask me what is AI, AI is a tool set of very different, let's say, algorithms. Let's see. One big part of artificial intelligence is planning. Planning is one of the big things in artificial intelligence. And for example, planning under uncertainty, Markov chains and things like that. Very traditional things already established in the 80s. Only the human is able to plan. Therefore, it is straightforward to take it as part of artificial intelligence. Another big part in AI is search in graphs, search in databases. You place a bot on the Mars and you have to find his way from A to B. That's a search problem and a planning problem. For example, A-star search and things like that are part of this pillar. Let's skip this for a second and talk about knowledge representation. That was for me always the most boring part of AI, but it's actually a super a very important part of AI, because if you have data, you don't have knowledge. So you have to transform data into knowledge. How can you do that? For example, with logical elements. If temperature is 20 degrees, if it is sunny, then I go to the beer garden. So you combine raw data with logical elements, and therefore you can represent knowledge instead of raw data. In the last, let's say, 15 years, there was not happening so much in this area, and the term AI was a bit overpromising, and people stopped talking about AI. But now we have a renaissance of artificial intelligence. Why? Because of one reason. The reason is machine learning. In the last 10 years, we had the big breakthrough in machine learning, namely deep learning. And I will give you an idea what deep learning actually is. I already gave this presentation to board members because it's important to really understand this, really understand what is deep learning and why it is so important. So these are the main technical pillars of artificial intelligence, and I will now talk about machine learning. In machine learning, we have a very traditional pipeline. We have on the left side the raw data, let's say customer data from guys who bought a VW and customer data from guys who bought a Porsche. That are features. I will give you an example. And then we take these features and train a model. That's the traditional pipeline in machine learning from a very top-level point of view. And how can this look like? For example, we have data like this in a database. We have, for example, from each customer the date of birth, the delivery date. We know from which country the customer was. We know other things like, for example, which engine. And we finally know what this customer was buying. One customer is buying a Porsche, one is buying a VW, and so on. Now the question is, if we now want to predict for an unseen customer, if you will more likely buy a Porsche or a VW, we now have to feed this into a machine learning algorithm. And the question is this the best way of doing it? Taking the raw data and feed a machine learning algorithm with it? And the answer is no. What we first of all have to do is, for example, is called feature engineering. There was a great talk yesterday from Zalando about feature engineering, and that is the daily business of a data scientist. He takes the data and tries to make a new representation out of it. For example, instead of dealing with the date of birth and dealing with the delivery date, we can create a new feature, which is called age at delivery, by simply subtracting both date formats, and we have a new feature based on the already existing ones. You can now imagine if you have dozens and hundreds and thousands of data of features, this became complicated, but this is the daily work of a data scientist. If we now have cleaned up and transformed all the data, we can now train a machine learning model where we have supervised learning. We have on the one side the VW clients, on the other side the Porsche clients, and we can now use, for example, a support vector machine and try to find a separating hyperplane. And we are now able for our unseen customer to forecast if this customer is more likely to buy a Porsche or more likely to buy a VW. That's straightforward. And now the question is, what is deep learning? From a top-level point of view, the only thing deep learning does is it includes the feature engineering, the manual feature engineering, into the learning algorithm. So instead of manually engineer features, we integrate it into the learning algorithm. So we try to transform raw data automatically to optimize the final classification result. How can we do that? And the answer is we use neural networks for that. And I want to give you a very short overview about the history of neural networks. Everything started in the 50s by two guys, McCullin and Pitts, and they solved the problem. It's interesting to read that paper. They basically tried to copy the human brain, put it into software, and everything is fine. And they came up with the Perceptron algorithm, a very easy algorithm with one neuron. You basically plug in the data, so each black dot is one data point, for example, the age, the other is the engine, and so on, and you try to solve the problem with one neuron. So this, people found out quite fast that this is very limited. You can only solve linear problems with this algorithm. So it is straightforward to say, okay, let's add layers. So let's add more layers, let's add more neurons, and so on, and so on, and so on. And finally, people find out that adding more layers does not contribute to the accuracy. So people added layers, but the result does not become better. And this was the so-called winter of neural networks. It was in the mid-90s when people said the idea of neural networks is dead. It's not working. When we add more neurons or more layers, we don't gain more accuracy in our predictions. But today we talk about deep learning with millions of neurons in it. What happened? And this is something I will tell you now. First of all, I will explain you how we train a neural network. So let's say we have a face detection and we map each pixel to one neuron in the input layer. So each single pixel is connected to one neuron in the input layer, and then we have the so-called hidden layers. This is a fully connected network. This means each neuron in the second layer is connected to each neuron in the first layer. Each neuron in the third layer is connected to each neuron in the second layer, and so on. And finally, we can measure what the network predicts, phase or no phase, 1 or 0. At the beginning, we initialize these weights, these blue lines, randomly with a number between 0 and 1. Randomly, okay? Any number between 0 and 1. 0 means absolutely unimportant connection, and 1 means this connection is super important between two neurons. Okay? At the beginning, completely random. We start with a stupid neural network. What we do then in training is we take one phase after the other and forward propagate it through the neural network. So it's called forward propagation. It's basically matrix operation, nothing fancy. And we measure the prediction of the neural network. So we know it's a phase, it should be a 1, but let's see what the network predicts. The network predicts 0.6, so we have an error of 0.4. What do we do with this error? We take this error, and this is now the trick, and back propagate it again through the network. So we take the error and say, okay, network, please adjust the weights a bit, that this error becomes smaller. And this is how this neuron connections change their weight, okay? So we take the error and back propagate it to change the weights in the network to make the predictions better. And each time we forward and backward propagate an example, the network have a better idea how to represent the problem. This is called backward propagation, one of the most famous machine learning let's say algorithms. It's 500 years old because it's a chain rule of differential equations. It's just a very nice mathematical setup for that. It's a super old thing, super straightforward and super computational intensive, and that's the big problem in deep learning. If the network becomes big, the back propagation is really complicated, and we need massive parallel hardware power like GPUs to accelerate that stuff. But I told you at the beginning that adding more layers doesn't make sense. So what was the problem? And this problem was discovered by a German professor, Schmidhuber. And I hope you have seen this wonderful visual effect here. What happens in deep neural networks is, if you backpropagate the error the gradient becomes smaller and smaller and smaller. So in the early layers of the neural networks, nothing changes during training. So that's the so-called vanishing gradient problem. So you backpropagate the error, but the error becomes smaller and smaller and smaller each time you go deeper into the network backwards. Therefore, you only learn in the last layers, but you learn nothing in the early layers of the neural network. That was discovered by Schmidhuber. And Canadian professor Geoffrey Hinton, he is now at Google, solved this problem by cutting off the neural network into small pieces, train each of the pieces individually, and simply stack it together. So instead of training the complete network, he cut it in pieces, you know, like a sausage, and finally he stacked together again the neural network again. And this was the big bang, 2006 in a Nature paper, and this is why now everybody is crazy about deep learning. So that easy idea enables us now to do really cool things. And let me sum up this here. Because it's somehow important to understand how what a network does. This network learns a representation of the data. So it is not about, so people very often talk about machine learning when they talk about, or say deep learning is a new machine learning algorithm. Machine learning is the smallest part of it. It's about finding a representation of the raw data without human interaction. So what you do if you do face detection is You start with a stupid network, and again and again and again, you train the network, and the network represents the data like you see here on the top. In the early layers of the neural network, you see that it basically learns blobs and edges and things like that. In the middle layers of the network, you see the network is able to see eyes. It learns that two eyes are next to each other, that there is an eye over a mouth and things like that. And finally, it learns prototypes of the face. This network has no clue that it is learning faces. It just sees pixel values, but it learns to see how a baby learns to see. So a baby also learns in this very biology-driven way, of course. That's a cool thing, but if you ask me, are we close to the human brain? We are light years away from the human brain. This is just matrix multiplications and exponential functions. And now to the point where I talk about the applications of neural networks. Of course, it's straightforward that we use deep neural networks for autonomous driving. So that's a very big business for Volkswagen, of course. I don't want to go into detail regarding technology. Of course, we use it for control of the vehicle. We use it for perception and things like that. And with the autonomous vehicle, I borrowed this slide from Alex, we are able to also provide our mobility solution to people who are currently not able to use it, blind people, old people, children, and things like that. That's a very interesting way of thinking about that. I have here a video for you, and I want to ask you the question when you see the video, which problem do you think this could be? What do you think, which kind of problem could it be? If you have an idea, just raise your hands. Okay, so this ugly video is one of the biggest problems every company will face within the next 10 years. This is server communication. And the biggest problem we will face in every organization is cybersecurity, protecting the infrastructure and protecting our fleet against hacker attacks. What we do in Data Lab is we provide algorithms and develop algorithms to support the security experts. We are not able to automate it completely. It's such a mess of data. It's 1 terabyte per day per sensor. 1 terabyte per day per sensor. And we develop algorithms to sort out the easy stuff and reduce the amount of data which we have to send to the experts. Cybersecurity is a big thing. We are developing cool algorithms to predict trips, for example, of our customers and to recommend, for example, routes and things like that. That's straightforward. Understand mobility. That's the big vision of Martin Hofmann, our boss. This is one of my babies, honestly. And this is how can we use AI in product development. Currently, in the automotive industry, and especially at Volkswagen, we think in 5-year cycles. Every 5 years, we have to develop a new Golf version, and this is how the company is driven. It's driven by 5-year cycles. And developing a new car is a super intensive thing, because it's super intensive and very complicated to simulate all that stuff. And we have created an AI solution based on deep learning to speed up the simulation process. Instead of simulation, we predict, for example, vibrations in a motor in parts by AI. I will show you that in a video. Everything you see now in the video is predicted by a neural network in real time. So this is an engine, and you see, the engineer is able just by a slider to calculate the vibrations in the engine in real time. Imagine you have to simulate that. It takes days. And now we can do it in real time because we have trained neural networks to forecast that. If we compare the AI predictions with a real simulation, we have an error rate of less than 1%. Less than 1% by using deep neural networks in this product development problem. And we can forecast things like vibrations, stability, and things like that. So this is my last slide. I love this slide, but I think you have seen slides like this a lot. The question is, can we do everything with deep learning? And to give you an answer here, I want to cite Julia. Julia have trained a deep convolution neural network to learn to separate images with fried chicken and Labrador babies, and the network completely failed. And so the message I want to give you here is, deep learning is not the holy grail, and it is not solving every problem, and you have to be super careful when you use it. Don't start with deep learning. Always start with a basic model. Okay, always first of all, clean up your data, use a linear model, then you have a baseline model, and if nothing helps, you can use deep learning. But this is basically the message I want to give you. There is no holy grail in machine learning. It's an exponential thing, testing thing. So that's it. We are the Data Lab, so everybody have a nickname. My nickname is Deep Daniel. I hope you understand now why. If you have any question, I try my best to answer it. Thanks for your attention.
Thank you for your very deep thoughts on deep learning and for presenting it in a way I think that even for non-AI experts it was easy to understand. Are there any questions from the audience? Any deep questions? So, if not, maybe I have a question. So, when you want to start working with neural networks and you do more statistics and normal machine learning before, what would would you give any hints, any advice, how to start and maybe what you should do and where you should avoid it?
So, if you want to dive deeper into deep learning, yeah, it's a really cool thing, then I highly recommend, for example, online courses. So there are great tutorials online, for example, fast.ai or Udacity courses. I don't like the Udacity courses so much. There are cool Coursera courses from Andrew Ng, for example. So this is a cool way to start and to get a basic understanding. What I can also say is, for example, our technology stack here. So there are a lot of libraries available and a lot of libraries around. I or not highly recommend, it depends on you, but our stack is TensorFlow and Keras, so this is how we develop our stuff. We are currently also developing a library where we use TensorFlow and Keras, but in parallel also PyTorch. PyTorch is also a cool thing, so maybe it makes also sense to dive deeper here. But if you want to start, I highly recommend to get familiar with Python, TensorFlow and Keras.
Great. And Daniel, but what kind of projects should you choose? And I mean, what are the project characteristics where it makes sense in your opinion?
Yeah, so deep learning is a general tool, so you can basically use it for everything. But let's say the natural thing for deep learning, is for example computer vision problems. So everything with images makes absolutely sense. Everything with sensor data makes absolutely sense. If we talk about data in a database, for example, so where you have a mixture of numeric data and nominal data, then in many cases, honestly, deep learning is not the best choice. Then we very often beat deep neural networks with random forest or stack methods or ensemble methods or things like that. So the best use cases for deep learning are really use cases with sensor data and especially images.
And how much data do you need to start with deep learning?
Oh, that's a good question, because I think everybody thinks he needs tons of data. That's not true, honestly. You can use, for example, transfer learning. You can use already trained models and retrain them with just a handful of examples. So you do not necessarily need huge amounts of data. You can use existing models and use it for your problem.
Any other questions before we close? Oh, we have now a bunch of. Did you sleep before?
Yeah, maybe just a quick question. Daniel, you were showing that you also started working with quantum computers. Can you, I mean, we can obviously have a whole session about this, but can you just give one or two examples what the advantages of a quantum computer would be and how it could change the way we use data and machine learning and so forth?
Yeah, I try my best. So I think what we have to understand is a quantum computer is not a faster computer. So that's not the case. I think people sometimes mix that. People think if you use a quantum computer, you can solve problems faster. That's not true. Quantum computing is not to make things faster. It is about solving, for example, NP-hard problems. So we can find an optimal solution for NP-hard problems. And where we use it, for example, is, for example, also in traffic prediction. So we try to predict traffic. We did that, for example, in China. Florian, my colleague, was, for example, in the lead here. And yeah, that's all about it. You can solve NP-hard problems with a quantum computer.
I think we had one in the back, yeah.
Hi. Could you explain a little bit more how you use AI for planning?
Sorry, for?
For planning?
Planning?
Like predicting the next VW Golf should be available in 4 years instead of
okay,
5.
okay. So, for example, in this mobility thing, we use, for things like that, so if you want to predict time sequences or things like that, we use LSTM models, for example, long short-term memory models, where we can model long and short-term behavior of data inside data, inside one framework. Yeah, also from architecture point of view, we use a lot LSTM models here in this domain. For example, if you predict the next trip or things like that.
Okay, great. Any last question? Yeah, over there.
Can you transfer all your knowledge from the deep learning also? You said that it's very useful for visual or picture processing. Can you transfer that also to acoustic problems?
Yes, of course. That's also a very cool use case for deep learning things. For example, speech. Speech to text, for example, is a classical application of deep learning. Also, for example, vibration data or sensor data. We use deep learning heavily, for example, in predictive maintenance of robots and things like that, where you have standard sensor data. This is a traditional thing for deep learning models as well, of course, yes.
Great. So thank you, Daniel.
Cool, thank you. Good.